Okay, that sounds good. We can begin in a moment. Jacob, just a heads up, if you want to take a look down the slides, I added a few diagrams to your section. And so if while I'm go over the first section, you can look over those, that'd be good. All right.
Yeah. Okay. I think that'll be helpful.
All right, swag.
Ooh, hello,
Um,
Paco.
hey Paco.
Hey,
Well, thanks for everyone coming in, and I have start recording now. Thanks, Paco coming in, and thanks Brian and Elham, to come and hear our two great presentations on model parallelism across GPUs. Uh, Yeah, so these are good presentations, I would say. I have heard those last night, for an hour and a half. I hope everyone can enjoy those. Take the lead, Ian.
All right, will do. Um, let me present my screen. The host has disabled screen sharing. If you could enable that real quick.
It is enabled.
Great.
For anyone who have questions during the presentation, just raise your hand in the emoji so that the presenter can call on you.
The Mozilla Firefox tab. Oh man, all of you can see it too. All right. Okay. So welcome to our presentation. This was a presentation worked on Sammy Hernandez, Ian Webster, and Jacob Wang. And we're going to talk about a paper that is about reducing the memory that you need to store activations for training your model. And we'll start at a very big bird's eye overview of your model like this. So your model is going to consist of your input, and then it's going to be passed to many different transformer layers, eventually getting you an output. The output of each transformer layer feeds in as the input to the next transformer layer. And that's essentially how the model looks at the largest scale. But then we need to zoom in a little bit because every one of these layers has a bunch of different sections in it. So let's take a look at each section. So here's the transformer layer, zoomed in a bit, and each transformer layer contains an attention head and a multi-layer perceptron, which also each contain even more sections. So now let's zoom in even more. Oh, right, and by the way, there's positional and word embeddings, and then output layer and loss. This would be what your model looks like if you only have a single layer, but you're gonna have a lot of layers. So usually when we're calculating the activation memory needed per layer, we do not need to consider the memory needed to store, the embedding vectors or the vectors for layer normalization at the end. So we're just considering a single layer at any given section of your model. So for starters, let's look at our input. So your input is going to be a matrix with 2 dimensions. And the first dimension is a sequence dimension. Every element along the sequence dimension is going to be associated with a word in your context window. So the sequence dimension can be as big as your context window, or it could be a single sentence, just as long as it's less than or equal to the size of your context window. That's how long it can be. The hidden dimension is all of the numbers associated with each word in the sequence. So that hidden dimension will contain all of your positional embeddings, which have been added to some constants that are normally associated with your word. So that's hidden dimension. But then we are not masochists. We do not train our models on a single sentence at a time. So we train our model in batches, which means that we have a bunch of these sequences within the batch. And so we send batches through the model. We'll do forward propagation, or like the forward pass through our model. We'll store the outputs to all the matrix multiplications that happen, or the inputs, I should say. Then when we come back and do back propagation and the gradient descent and whatnot, we're going to use all those stored inputs to the matrix multiplications to calculate the gradients, and then the gradients will be used to calculate how we should update our model's parameters. So let's take a look at what it takes to store the memory for the activations. The goal for this section is that we're going to derive an equation that will tell us how much memory in bytes we need to store for activations for a given size of input, with, you know, the sizes being hidden dimension length H, batch size length B, and sequence length S. So you've got your input batch, it goes through your layer. And so the first section we're going to look at is the attention. Oh, sorry, my bad. The layer normalization. Each of these is going to contribute S times B times H worth of activations, but not so fast. We can't just, yes, Zishan.
You have mentioned activations many times. What is exactly an activation?
Right, my apologies. So an activation, so if we look at this transformer model, we see a lot of different colorful blocks in here. And each one of those blocks is generally going to signify a sort of matrix multiplication or an activation function that has been applied to the input as it passes through the transformer. And the reason why, so activations are the inputs to those matrix multiplications or to the activation functions. And the reason why we store those is because those, when we do backpropagation, will then be used to calculate gradient descent.
So we need to store all these intermediate values. So when we're doing backpropagation, we can utilize those values to calculate our gradient and do the weight update. Is that correct?
That's right. Yeah, precisely. Okay, yeah. So hopefully that makes it clear. Now we can continue. So the layer normalization section of your transformer layer is going to need S times B times H activations to be stored. So in your memory, you need to make space for this many activations. But we're trying to derive an equation here, so we can't just look at the number of activations. We have to look at the memory they take up. And in this case, for this paper, each element for the input to the layer normalization is going to be worth 2 bytes. So actually, the memory needed is 2 SBH per layer normalization. Yes, Zishan.
Can you explain why it is 2?
I believe it's because they're storing 16, like length 16 floating point numbers, and I think that takes 2 bytes. I'm not actually sure though. I don't know binary.
Yeah, that is the answer. And if the model weights are stored in FP32, then it will take 4 bytes to store each number. If it's in 8, then it will only take 1 byte.
Yes.
Yeah, thank you.
Awesome sauce. Also, at any time, if you guys have a question, please feel free to unmute yourselves and just, let it rip. So, yeah, so the layer normalization is going to require 2 SBH, and as a reminder, SHB, that's the dimensions of your matrix, how many elements are going to be inside the input. And you're going to need to store that many bytes worth of information. So next, let's take a look at the attention head. And within the attention head, if we blow it up, we're going to see something like this. It's going to go through a linear layer, which is going to produce these K, Q, and V matrices. Q and K are going to undergo a multiplication operation. There's also a transpose, I think, but we don't need to worry about that. And then that's going to be pushed through a softmax, a dropout. Dropout is going to be a matrix multiplication, except every single value in the dropout matrix is going to be 0 or 1. So when we get to the dropout part, you're going to notice that it does not have a multiple of 2 in front of it. And that's because every single element in the dropout matrix is going to only take 1 byte instead of 2 bytes because they're so small. They're just zeros or ones. But I'll remind you of that later. And then there's an additional operation here, which gets you your output to the attention head. And now let's narrow in on each part. So after you do your linear section, the outputs are going to be 2 SBH, are going to require 2 SBH bytes to store for all these operations. Then the Q times K operation is going to take 4 SBH to store because also I should specify, remember the activations are associated with the inputs to each one of these operations. So, this X symbol is an operation, the softmax is an operation, the dropout is an operation. So the activations, the number of activations is associated with the size of the matrix being passed to each one of the operations. So the size of the matrix being passed to this operation right here is 2 SBH, and then you need to multiply it by 2 to get the number of bytes. Okay, so now we've done that. Then the amounts associated with softmax and the dropout are going to be 2 S squared B and S squared B, except wait, that's not true. Because this is multi-headed attention. There's a bunch of these, which means you need to multiply it by A, which is the number of heads. And then finally, we have this operation, which is going to take in values from this arrow here. So V contributes the 2 SBH part of this equation. And then the dropout, the output of the dropout matrix is going to contribute this part. And now there's 2 more things we need to consider before we're done. We also need to consider the dropout mask. And the dropout mask is the same as the dropout matrix I had mentioned earlier. It's composed only of zeros and ones. And so you don't need a factor of 2 in front of it because every element is only worth 1 byte. And then also we need to consider the inputs to the linear layer, which are all identical. It only takes 2 SBH. So now, in total, the amount of memory needed for the attention head to store the activations until backpropagation is this expression. Yes, Ishan.
So in this slide, it seems like, well, obviously that for the S square, it is a very big part is in quadratic time. Yeah, in quadratic scale. So when we're having more sentences, even longer sentences, context window, for example, 8,000, then the memory required to store these will be also quadratically grow in memory.
Ooh, that's important. Yeah, that could be nasty if you had a very big context window. All right, cool. So now let's take a look at the next part. So again, this is the transformer layer. We just looked at the attention head, and now we're looking at the MLP block. The first operation in the MLP block is a linear one. It takes the hidden dimension of your matrix, and it's going to turn that to 4 times its size. So the input of this block is going to be the size of your input matrix, but the output of the linear block is going to be 4 times that. And so since the input to this operation is the size of your input matrix, you then just need to multiply that size by 2 for the bytes. Next, for the activation function, this one's called GELU. I forget what GELU does to all of your values, but it does something. And it transforms the size. It doesn't actually change the size of the matrix. It's the same input and out. But since the output of this operation is 4 times the size of your input matrix, you then end up with 4 SBH activations that are going into the activation function here, GELU. So 4 times SBH, and then you need to multiply it by 2 because of the bytes, and you end up with 8 SBH bytes of memory needed to store the activations for this layer. Then next, we have another 8 SBH needed for this layer, and only SBH needed for the dropout layer, because again, the dropout matrix is only made of zeros and ones. You don't need to multiply it by a factor of 2. It only takes 1 byte an element. So the total for the MLP block ends up coming out to 19 SBH bytes. I feel like I got to add the units here. And then if we sum everything together, the attention head contributes this much memory, the MLP block contributes this much memory, and the normalization layers in between contribute this much. Sum them all together, you get this equation. So that is the memory per layer that it takes to store the activations until the backward pass begins. But now, that's a lot of memory. Maybe you're operating on a device that can't actually store that much memory. So what you're going to want to do is you're going to want to take the sections of your transformer block and you're going to want to split them apart onto different devices so that you don't need to store as much memory, don't need to store as many activations on one device. And that's what we're going to get into next. This is just a quick overview. Oh, yes. Device in this case would refer to potentially like a GPU or a collection of GPUs. Yeah. Not a CPU because you're not really doing this kind of stuff on CPUs anyway, but yeah. Okay, cool. So that's a summary of the activation memory stuff for the transformer layer. And now let's talk about tensor parallelism. So tensor parallelism is the first trick you're going to employ to split up the operations within the transformer layer. And also, just again, overview, this is the transformer layer, this whole thing together. It's not a single layer. So let's say your input matrix looks like this. It's just a S by H by 1 matrix. And then let's say you need to multiply that by this massive matrix, the tensor. It's going to be a matrix multiplication, but you don't want to store all the activations for that on one device. What you can do is you can split your tensor matrix, this is the tensor matrix, across 2 devices. And then you're going to take your input and you're going to send it to each device, the identical input to each device, and you're going to multiply that by just half of that tensor. And so each of those tensors will then output a smaller matrix, and then you're going to combine those at the end, which with a kind of communication I believe is known as all gather. And that way you can not store as many activations on one device, but end up with the same final output matrix. Just as kind of like an overview model, right? Here's that layer we were looking at before. I know the graphics look different, you know, different colors and all, but that's the same as that big block we were looking at. And then here you see outlined, dotted, are the sections that we're going to use tensor parallelization on. So we're going to split these matrix multiplications apart onto different devices, and that's going to look like this. Bam. And you can imagine little lines flowing from here to here, and, you know, here back to here, and whatnot. Okay, so that is tensor parallelization. And that's going to take our equation for activations per layer, and it is going to split a large portion of it by the number of devices you have available. T, by the way, is the number of devices you're splitting your tensors across. And in this case, it's 2. So you can imagine substituting in 2 for T here. Yeah, so that's what that variable means. You're probably noticing that there's this 10 out in front. And the 10 out in front is because some of the operations in our layer don't get split like this. The big tensors are in the neural network parts, these parts do not need to be split like that. And so they are not going to reap the benefits of tensor parallelization. But we can do something. Oh, yes, Elham.
Hi, yeah. So I have one question regarding this splitting. So you just gave an example of example with just one kind of it's just bat size equal to one. Now, if in this case, like in this generic equation, you have like a large batch size as well as there are multiple heads. So is there any preferred way of splitting? Like, if you have the batch size of, let's say, 1,000 and then you have many heads, how do you split? How do they split across different devices?
So you mean like how would you split your tensor matrix?
Yeah.
This one?
Yeah. Because for example,
Well,
like here the schematic is just batch size equal to one, and this is just one head, right? So now in reality
right.
there will be many heads.
Oh, there would be many heads. Good point. So I'm just imagining this as one matrix, but if you had many heads, you'd have a bunch of these. So this thing you'd probably have, if you can imagine, just 15 of them stacked below it. And I'm guessing the way you would do that is you would just split them in half, all of them in half, and then allocate them to however many GPUs you had available. So if you had 2 GPUs, you'd split them in half and put them on half of all those matrices of the different heads on GPU 1 and half of all the matrices that were in the attention head on GPU 2.
So are they splitting always in the direction of hidden dimension, or they also sometimes do other tricks?
So you mean like could you split it like hamburger style rather than hot dog style, kind of like this?
Yeah. I don't know what exactly, because I haven't read the whole paper.
Yeah.
So I mean, this is like this example schematic shows like you're splitting in the direction of hidden dimension, right? I mean which makes sense, but I don't know if
Right.
Yeah.
To be honest, I don't know. That's actually a great
Okay.
question. I bet you can. And I bet you could split into like 4 pieces instead of 2, allocate to 4 GPUs. That'd probably be fine as well. I have not actually
Okay.
looked into it, but yeah, you're probably right.
Okay. No.
Well,
Okay. Yeah.
adding on to that, for cutting through like an hamburger style, it is not efficient in my opinion because you will
Okay.
need to pass the intermediate values, pass the activations to the next piece that is hosted on a different GPU.
Yeah, I think it makes sense to split always in the direction of hidden dimension. But I don't know if other people do other tricks or not. I actually
Wait,
don't know.
wait. No. That is, I'm not too sure if I understand correctly what you mean by across the hidden dimension. Here
Because
is you.
This
um,
long section is a hidden dimension here. Here is S, I guess, in
Okay.
this example.
Yeah, and another reason why you can do this tensor parallelism is because, I mean, these are binary addition. These will just be equivalent by adding them together once you split them apart. And the reason why you can split them in a half because they're all big linear layers, and it is very easily that you can split them in half. For example, the MLP, there are 2 linear layers, and then for
mhm.
attention, there's attention heads that project, and these are all linear layers.
Okay. Anyways, good stuff. Thanks, Ian.
No problem. Thanks. That was a good thing to point out. I am now curious as well. So yeah, you split it across GPUs. You could have more than 2. You could split it a lot of different ways. And then that takes your equation from this to that. And that is tensor parallelism. But again, there's still some sections that have not been parallelized that way, like the dropout matrix, layer normalization, stuff like that. But if activation memory for those sections that haven't been parallelized becomes a concern as well, there is another trick you can use, which is called sequence parallelization. And it looks like this. Jacob, I made this slide actually without your consent. But you can start now if you want, or you can have me walk through it. It's up to you.
It's all right. I can walk through it though.
All right, cool.
Yeah, I believe. Oh, is this slide for intended for sequence parallelism or just so like? the stuff
Yeah,
that you were-
this is still a sequence. This is sequence parallelism now. So instead of having the matrix getting split, you're having the input get split.
Yeah. So yeah, can you go to like slide number 36? Yeah. So the important part of sequence parallelism is we're splitting the parts between like the tensor, the part that we parallelize in the tensor part. So if you look at the blocks that says sequence parallelism, we're parallelizing like dropout layers and layer norms, like these two parts, and we're like shredding them along their sequence dimensions. So we're also splitting those into like different like GPUs, so that they can be like processed individually and also like reduce the memory per GPU. And before and after each of these like sequence parallelism sections, we also have the an all gather like operation and a reduce scatter operation to like kind of like distribute and combine all the data from each GPU. So in this like method, our activation memory per layer is going to be like the equation at the bottom. Yeah, and moving on to the next slide. Yeah, I think this is pretty much like sequence parallelism. Sorry, I really apologize for not having like a good like visualization. But if you guys have any like questions, you guys can ask. Yeah, and yes,
Sorry, I have a question. So you said sequence parallelism is split the input into half. But how exactly do you split? Do you split across batches? Do you split across hidden dimension or?
Yeah, I believe like it splits along the sequence dimension, which means we're keeping like the sequence intact for each of the GPUs, right? So we're splitting across like the batch dimension, I believe,
Okay. So
or
split
is it like
across the batch,
yeah?
but for each piece, you keep the entire sentences so that you can do your attention onto each other. Is that correct?
I believe like in the paper it says like you're not like for sequence parallelism we're not parallelizing the self attention part. We're only like parallelizing like the part between like the self attention and MLP, which is the dropout and layer norm, and those take up a lot of like memory.
Mhm.
Yeah, so I'm not sure. Like I don't think this is like the sequence parallelism slide. Yeah. So
Okay, yeah,
right.
I think I got it. Thank you.
Just quick follow-up on Jishan's question. So the picture that we were showing earlier with the 3D blocks, you get back up to that one. So
Yeah.
that one. So you were saying that I think the S dimension was the vertical dimension. So
My bad. I might have made a false diagram here in
okay,
terms of which dimension it gets split by. Yeah, so I
that's
mean,
fine.
I was thinking vertical dimension is S dimension, this dimension's H dimension, but I did not consider that there would be a whole batch and maybe you split it along the batch dimension or that you'd split along the S dimension. And yeah.
So if we were splitting along the S dimension, then it would be splitting, I can't really describe it. Yeah, along that diagonal. Yeah. Okay, thanks. And the other question I had is on the G hat function. Can you talk about that? So I think what you're saying is you're splitting, let's say, the sequence, and you get like y1 and y2, and then you basically have to distribute all those results, combine them back, so each of the tensor parallel blocks gets y, right?
Right. So
But I don't
yeah.
understand what the G hat one is doing, because it looks like you've got W1, W2, and also a W1 and W2. So what operation's happening there?
It's I believe it's a operation where, like for the G hat though, we're collecting all the data from each GPU, and then we're like we're gonna prepare them like ready for our sequence parallelism. So we need to like distribute them in a correct way, so that the data is like split along the sequence dimension.
I can follow up on that. So G means all gather, and G hat is all reduce. So basically, what these two does is that in their forward pass, so for example, G will distribute your sample across to different GPUs because different parts are hosted on different GPUs in your forward pass. And then in the G hat in your forward pass, they will combine each devices will talk to each other to combine all the different pieces together, right? And then and combine, and then you can move on to next layer. And during the back propagation, the G hat will will distribute again to all the devices onto different GPUs because you are doing weight updates. You need to pass your gradients, and then for the G in the back propagation, it will combine all the values and then pass it back to previous layers. So G and G hat are serve as you can think of those as GPU communications to passing the values across GPUs. Does that help understanding?
Possibly. I'll take it offline. Thanks. I get the general idea, but usually reduction is a vector to a scalar, and so I don't really understand what you're saying there. But
Oh, probably they refer to different terms. Gather and reduce in here. We can talk later.
okay. No, go on. Thanks, guys. That's great.
Yeah. Right. Then I believe like right. So then should we move on to like the next part, which is pipeline parallelism?
Yeah, sure. All right.
Yeah, I think.
Thank you, Jacob.
Yeah, I think. Yeah, I can go over it. Like since Sammy is not here, so I think.
Sure. Yeah, if you want.
Right.
So just as a heads up,
yeah.
these is what the slides look like.
Right. So yeah. So like, yeah, you can just start from there, like slide 39. Yeah. Can you also like display all of the GPU numbers? Oh, actually, yeah, slide 39. Right. So in pipeline parallelism, we're like dividing the layers, like different layer of the transform model, like into different groups. So each group can have a couple of layers of the same model, and then we're distributing like these groups, each group to like one GPU. And basically like one GPU is only like in charge of like processing the data through the several layers that it is assigned to. So moving on to the next slide, here's a good illustration of the pipeline like diagram. So like each of the blue like grid that you're seeing is a micro batch So meaning that it consists of like the entire like sequence dimension and also like hidden dimension of a batch. So if you go through, so let's say let's start from device 1. If you look at like right, so micro batch 1, it goes through device 1, meaning that device 1 will like first inference the first several layers of device 1 and move, and it does a communication to device 2, which sends its output to device 2, and device 2 also let it go through the several layers, and then eventually goes through like device 3 and device 4, and then it completes like the inferencing, at which point like we'll move on to like back propagation of each like micro batch, which are the green grids. So if you look at the green one, and then like and so on and so forth, like all the way like from device 4 back to device 1, we're doing the same like communication, except for like it's in the opposite order, right? And all for all of the gray like grids, it's called like pipeline bubble, where the devices are like idle and not doing anything, right? And like the activation memory for like per device is going to be like this equation like below. And yeah, I guess we can move on to the next slide.
Well, at this point, this slide I think is going to be about selective. Oh wait, no, this is about something different. But after this slide, then it'll be like selective activation recomputations. So this part I can take care of.
Okay. All right. Thank you, Ian.
Ooh. Okay, so right, just as a summary, tensor parallelism, you're taking those sections, you know, with the big tensors, and then you're splitting them across GPUs. Sequence parallelism, you're taking the stuff that doesn't take that much effort to compute, you know, like some small layer stuff. You're going to split those across GPUs. And then pipeline parallelism, you're taking your layers and you're splitting those across GPUs. Yeah, and so the equation we have at this point is this one here. L stands for the number of layers you have. And so the reason why we're multiplying L by this expression here is because this is an expression for the very first stage of your pipeline. And the first stage of your pipeline will be over here. That stage has to include things like the input embedding vectors and a bunch of other stuff. So it's going to have it's going to demand the largest amount of memory of any of your stages. So we really consider that one, except we lied to you. This is not the equation. You see, you have all these other vectors associated with, like I said, the position embedding stuff and the output loss function stuff and blah, 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 blah. That stuff is not accounted for. And that is accounted for by this equation. This sigma thing right here, let's just take a look at the sigma. That part is going to be equal to 1 if the stage we're considering is 1. Or no, sorry, that's going to be equal to 1 if there's only one transformer layer. So like this diagram, if there's only one GPU with one layer, then sigma would equal 1. But if there's any more layers, then it's going to equal 0, and this whole term's going to cancel out. And that's because this term right here represents the activations associated with all this output stuff. And because, again, we're only looking at the first stage does not need to worry about all the output stuff unless there's only a single layer. Which means that this part, if there's any more than one layer, is going to just cancel, and you're just going to be left with this expression for the activations that are associated with the initial like position embedding, stuff like that. And so even if you have like all this stuff here is present, it's only going to amount to like fractions of a percent of the total memory needed to store the activations for everything else. So we really never even consider this equation. As a matter of fact, we did not even need to mention this slideshow. Sorry, I'm just reading the stuff that Zishan sent in the chat. Zishan, if you want to unmute and mention that to the whole group, that might be good.
Yeah, sorry to interrupt. The sequence parallelism splits across the sequences because when, for example, we can split a full sentence into two halves, the first 10 words and the second 10 words into different devices because those layers are sequence independent. So this is possible to do that. And once we get into sequence dependent layers, we combine and then do tensor parallelism.
So what you're saying is this long direction here is like the sequence direction? Like
Yes. This is correct, yes.
So the way it gets split is you like in the middle of your sentence, it gets split in the middle of your paragraph?
Yes, because you are passing into sequence independent layers.
Ah. Okay, so that makes sense. So then this would be half of the words, this would be the other half of the words, and then it get processed by identical matrices in different devices.
Yes.
Swag. Okay, cool. Right, so this part, I kind of wasted your time here. You didn't need to know this. And then now we're into a new section of this paper. So now that we've spent all this effort parallelizing our computations and we've saved all this memory, yay for us, now we're going to want to start doing something called activation recomputation. So with activation recomputation, instead of using any of that memory, we just put all the effort storing, saving, we're not going to use any of it, and we're going to recompute all of the activations. And the way you can do this is you save just like one layer of activations for I think every operation or something like that. I don't remember exactly how, but you're able to recompute all the activations by just storing a little bit of them. And then that means that you do not need to worry about not having enough memory on your device to run your model. So that's great, but it is a huge pain in terms of computation time. It can increase your computation time by like 30 to 40% to have to recompute all of those activations when it's time to update your model's weights. So what you can do to instead to get the best of both worlds by saving memory and saving computation time is by only recomputing some of your activations and then storing the rest in memory. So you want to store as many activations as you can in your memory and then just recompute some of them. So there's a lot of different ways you can do this. And by the way, this equation up front here, that is the amount of memory it takes to store your activations if you only if you recompute all of them. So if you recompute all of your activations, I mean, you still need a little bit of activations, but this is the amount of memory you need. And as you can see, is not very much. Oh, it also assumes that you're not employing any parallelism, so no tensor and no sequence parallelism. This is just the memory per layer needed with no parallelism and full recomputation. Oh, yeah. So, continuing to talk about the selective activation recomputation, the selective part refers to the fact that you can select certain activations to recompute and then store the rest. And there's a superior way of doing this. So the best way of selecting activations to recompute is by choosing the activations that take up the most memory, but take up the least amount of time to compute. And those activations are associated with these operations in the attention head. So the activations that process this V vector and do the softmax and dropout, those take up a huge amount of memory because I believe the numbers inside of them are rather large. But they only take a extremely small amount of time to compute. So to get the best of both worlds, you will just store all the other activations of your layer and then just recompute these activations. And this, if I remember correctly, is going to save you like 60 to 70% of your memory or something like that, and save you a very large amount of computation time. And so after doing all of that, your memory per layer looked like this before. This term, I'm drawing a blank. I don't know what that term means. What happens? Oh, yeah, that's the term I believe associated in large part with the attention head, these operations here. Oh, actually, that might be the thing that Zishan pointed out earlier, the one that grows exponentially or quadratically. And so that's why that term is a huge part of your expression. But when you choose to recompute these later on instead of storing them, that term goes away. And so you are left with just this expression for the total amount of memory needed to store your activations for updating your weights later on. So this is the final formula for how much memory it takes to store your activations per layer. And that is also the final slide in the presentation. Have a good one.
Wow, it's
Actually,
amazing.
questions first. Yeah, thank you.
It's great presentation. Yeah, it's really, really good, really good.
Appreciate it.
Thanks for spotting out that the quadratic term. And it is very important actually, because it is S square, S means sequence length square, and it is the biggest part for memory when you are scaling out to longer sequences. And this is mostly the memory bottleneck. And people have been trying many methods to distribute that quadratic term across different GPUs. However, empirically, we'll discover that it is even faster to recompute the S squared term, because the S squared term is the Q multiplied by K transpose, and that is, you only need very little memory to store, for example, Q and K independently, instead of storing their output, which is S squared. Right, so by doing the recomputation, it's even faster and it takes less memory. Yeah. Good point, Ian.
Okay, cool. So that is end of the presentation. And if you guys have any questions, now's the time. Okay, cool. That's it. Have a good one, guys.
Thanks a lot. That's great.
Yeah, thank you both Ian and Jacob, and Sammy, who is at the back of the screen, who is not present today. Great work, everyone. Really informative, and I really like how you draw out each step by step with your visualizations. It helped a lot.
Yeah, it was great pictures. So
Okay, are we ready for the second presentation, or does everyone wants to take a little break? Well, it seems like we're very enthusiastic about the second presentation. Take your lead, Rouge and Yalu and Arnav.
All right. Good evening. My name is Yano Ouyang, and together with Arush and Arnav and Henrik, who unfortunately was unable to make it here today due to circumstances, we will be discussing giving a short introduction on how to do large-scale model training with the Megatron LM framework. So the motivation for this is basically because present-day large language models have billions upon billions of parameters, with Llama 3 having 70 billion. There is absolutely no way that this will be able to fit on a single device, a single GPU. So obviously, this needs to be computed using an array of GPUs and servers. Thus, this introduces a lot of intercommunication between these hardware devices, and that could potentially slow down the training by a lot. So there needs to be a way to efficiently organize how these hardware interact with each other for best performance. This is where Megatron LM comes in. So it is a framework that utilizes various parallelism to ensure that large-scale model training is as efficient as it can be. So regarding parallelism, we'll be discussing three different types of parallelism: data parallelism, and tensor parallelism, and pipeline parallelism. Data parallelism basically boils down to having the exact same model on different devices. Let's say you have 4 GPUs available. Then what you're going to do is you are going to duplicate your entire model on each of the 4 GPUs. And then when you take your input data and batches them further, so each GPU would receive a different image or different input from one of the data. Then you would compute the weights and the activations in the forward and backward fast independently on the 4 devices. And periodically, you would take the weights that are obtained on of these individual devices, aggregate them, and use and most of the time take the average to ensure that the model behaves similarly across all different devices. This is to eliminate potential outliers that are just so different from every other model. Now, regarding how you would aggregate these weights, there are 3 methods you could go about it. What you see right here is a basic model of having a 4 GPU setup. And there is a PCIe switch in between the CPU and GPU. That's because most of the CPUs don't have enough channel to handle the GPUs. Thus, it needs a PCIe switch. Now, you could compute the actual aggregate the weights differently. You could do that in the CPU. You could do that in one GPU, or you could distribute them across all the GPUs. This method is the least inefficient because you would actually need to go from the GPU to the CPU 4 times. If we were so if we have a PCIe of speed 16 gigabytes per second and the weight itself is 100 megabytes, then this configuration would mean that we need 40 microseconds in total to transfer the weights from the GPU to the CPU, and another 40 microseconds for the weights to be updated on the and transfer back to the GPU, 80 microseconds in total. In this configuration, we will be calculating the aggregating the different gradients on a single GPU. And thus, you would only need to transfer weights from 3 other GPU to this one. So 30 microseconds for in total for the 3 GPUs to go to GPU 0. 30 microseconds go to the weights to be accurately updated, and thus this will take 60 microseconds in total. So it's more faster than having it done in the CPU. There is also another way of doing it distributed across all GPUs. So remember when I said we had a weight that's 160 megabytes in size? Well, we could partition that further into something like 4 times 40 megabytes. Now, the PCIe standard allows parallel computation, meaning that the GPU can both send and receive data at the same time. So if we were to boil it down further, we would actually have, I believe it is 7.5 microseconds to transfer the weights from all GPUs together, and another 7.5 microseconds for them to be updated back to their original devices. So as you can see, the different configurations for the parameter server would result in pretty significant changes in the overall computation speed. Next up, we have pipeline parallelism. As you could see on this graph right here, essentially this breaks down your complete neural network into different stages, and then it would assign these stages to a physical device or GPU. This way, the inputs would go through all these different stages, and at the end, and adjacent devices will communicate each other during forward pass or backward pass to either update the activation or the loss gradients. Now, this can be seen in this way. Suppose F is our data input. We would first process the F going to stage 1. Then after it's done, the output from GPU 0 will be fed into GPU 1. The output of GPU 1 will be fed into GPU 2, GPU 3. So this here is the forward pass. Now, in this place here, we will be. Oh, sorry. Please go ahead, Zixian.
Why do we need to pass to different GPUs? Why can't we just use GPU 0 and use it all the way through?
That is an excellent question. The reason we use pipelining is because it's very likely that we will not have enough memory to store the entire neural network on a single GPU. You can see right here. Suppose the GPU 1 can only store like 18 different nodes. Then if we have a neural network with a parameter, say like a couple of billion or stuff, we cannot store that the complete neural network on a single GPU. Hence, we need to slice it up and to place it. This is due to hardware limitations. Does that answer your question?
Okay, I have a second question. You
All right.
mean not large enough to store the entire model onto one GPU. If in the example you gave, you said that we have, let's say, 10 billion model. If each parameter is 4 bytes, FP32, we have 40 gigabytes of memory used. And if we have a MI210 that is 64 gigabytes, it's totally capable of storing that large of a model. So I'm asking, is it not enough space to store the model weight itself, or store the activations that used for updating the weight?
I suppose it will be the activations.
Yes. Activations is much, much larger than the model weight itself. And that is why we need to store different layers across different GPUs, and thus we do the pipeline.
I see. Thanks for
thank you.
clearing up that. Going back to this graph, as you can see, I was about to mention the back propagation process. So in this process, the gradients are calculated and updated, and the output of this backward propagation itself is passed forward, just like in a neural network. Essentially, if you think of the neural network at this point as the very entry of the neural network, at this point as the output, then this is just passing all the different gradients and weights and updating the weights forward. Now, this is a trivial version of this, but as you can see, there are a lot of gray blocks here. These are what we call bubble time, and it means that hardware is idle. It's not doing anything, and that's wasting the performance. So what we want to do is minimize the gray spaces, the bubble time, so that we are utilizing the hardwares more efficiently. Now, one thing we could do is that we could break down these batches further into micro batches. Say if you think of this as an entire batch, you could break it down into 8 smaller batches. And you can see here that you don't need to process the entire big batch before it is passed on to the subsequent devices. Thus, you can see here, the gray areas are reduced somewhat. So, we could also use, we could optimize this further. These are different methods of optimizing the pipeline. It may look a little bit complicated, but you just need to understand that what they are all trying to do is to minimize the appearance of the bubble time, the gray blocks, so that we are all using the device as much as possible and not just leaving them and letting them sitting idle. Right, so this is a model pipeline parallelism. Finally, we have tensor parallelism. It is very similar to a pipeline parallelism, but while pipeline parallelism splits your neural network according to the layers, let's say, I would say it's horizontally, then tensor parallelism splits your neural network layer vertically. As you can see here, this is why we are able to do so, because if we think of a general multi-layer perceptron block, this is what MLP block does. And since the general matrix multiplication can be represented as this, then this means that we could split our entire neural network in a similar fashion. This is a more in-depth example. So looking at this multi-layer perceptron block, you can see that the A currently stands for the model weights, the X stands for the input, and the Y is the intermediate output for dropout. Naturally, a multi-layer perceptron block will we have Y equals G lu XA. But we could actually split the A into equal partitions. And due to the nature of G lu, this is what we'll be getting. So this is a mathematical proof of why we could split it up vertically, as to speak. Now, using that, we could also split we could also split transformer block accordingly. So, so we could give it different key value queries here, and the feed-forward neural network, feed-forward network is the same as what you get with MLP. Now, with these operations, notice the F and the G values here. These are necessary steps that you need to take to either split the original input or to combine them. You would do that in a process called the all reduce. Basically, you would go over all inputs of your inputs and combining them in a way. So operation like the max, min, sum, and these are all reduced functions. We could represent this. We could represent the allocation of these with the hardware like this. So as you would see here, this is a very big transformer block layer, and the blue lines would indicate some the weights, the estimations, and the general structure that would be stored on a single device. As you can see, we could split this transformer layer vertically and store it on two different devices. Right, that's it for the general introduction to parallelism. I'll be handing over to Arusha to talk about I'll be handing to Arnav to talk about the performance analysis.
Right, we'll wait for any questions if there are any. Fantastic. Thank you, Yalu, for giving us such a thorough introduction to all different forms of parallelism. And in this part of the presentation, we will be considering the implications of combining different models of parallelism that Yalu just described into one model. We will mainly focus on trade-offs between memory footprint and the number of communications that we need to make in order to implement these models. Before starting, I just want to, for the sake of correctness, I just want to state that the paper clearly states that the quantitative cost models that are provided here for time are not direct models because it's extremely difficult to model precise direct models given the difference of bandwidth in the interconnects between GPUs and the interconnect between servers. Therefore, all the math here, although extremely representative, is just to give a general idea of the cost functions related to these models. Also, Yalu, my slides have animations in them. So when I say next, like just go to the next animation. Please don't skip the entire slide by mistake.
All right.
Right, thank you. So just before we dive into a little bit of the math regarding the analysis, let me quickly introduce all of you to a little bit of notation. Starting with small p, small t, and small d. These are just the parallelization dimensions, where p is the number of dimensions for the pipeline model, t is the number of dimensions for the tensor model, and d is the number of dimensions for data parallelization model. N, the small n here, represents the number of GPUs we will be using. In the paper, it has been set up such that P into T into D, as in the multiplication of all three dimensions, is equal to the number of GPUs being used. Capital B here represents global batch size, which is the size of basically the input. B, small b here, represents the size of each microbatch. Now, microbatches are just, as the name might suggest, small pieces of the batch. The batch is divided into smaller pieces for easier processing. And small m here represents the total number of microbatches that there are in each pipeline. Can we go to the next slide, please? Okay, so here we have bubble time fraction, which is also known as pipeline bubble size, or as Yalu also mentioned, bubble size. Now, bubble size, the name might be slightly misleading to actually what it represents in its mathematical form. So we'll go over that a little bit here. First of all, I will describe a few parameters here. So TPB here is the time it takes to process one microbatch. So if we have P dimensions of parallelization, of pipeline parallelization, as in the model has been, the neural network has been divided into P pieces, you can easily see that one GPU will need to transmit its, so one result will need to be transmitted P minus 1 times to all the P minus 1 other GPUs. Let's say each forward pass takes TF and each backward pass takes TB, which means the total time to process one microbatch would be P minus 1 times TF plus TB. Next, please. Now, here we have the ideal time to process an entire batch, which is M microbatches. So here you might see that the ideal time has been given by M times TF plus TB. But you might ask, Arnav, you just described that the time to process one microbatch is given by P minus 1 times TF plus TB. So how is it that the ideal time to process all the microbatches is M times TF plus TB? Why is it not M times P minus 1 times TF plus TB? Now, what we have to remember here that TID is the ideal time. The ideal time to process M microbatches. This ideal time is assuming there is perfect overlap and there is no idle time in any of the processes, which is certainly not the case most of the times in pipeline parallelism. As you can see in figure 2, the top figure here, while device 1 is working on the first microbatch, device 2, device 3, and device 4 are idle. Device 1 works on the second microbatch, device 2 works on the first microbatch, device 3 and 4 are idle. So basically, at the start of the process, when the first few microbatches are entering the pipeline, the latter stages are idle. And at the end of the process, when the last few microbatches are completing their backward passes, the earlier stages are idle. That's why the time to process a microbatch is not actually equal to the ideal time that we would like a microbatch to be processed in. Next, please. So what is actually bubble time or bubble time fraction? Bubble time fraction is nothing but the fraction of TPB divided by the ideal time, which basically represents is a measure of how long the machines are sitting idle. We want to minimize bubble time as much as possible. So that's basically an overview of what bubble time is. Next, please. Now, all reduce. All reduce is something that Yalu also referred to. It is something that tensor parallelism uses for each and every layer. And since this is extremely crucial for the next part of my presentation, I thought I'd quickly give a small overview of what all reduce is. So while training a model, every process or every worker/process here basically represents one GPU. So every process or worker needs to communicate its results with every other process or worker. Next, please. So what do? We do exactly what I said. We share each process and worker shares its data with all the other processes and applies a reduction operation. Now, why do we apply a reduction operation? There can be many reasons for that. One of the reasons might be that it's extremely inefficient or extremely memory inefficient to save the inputs of all the processes. Let's say 4 GPUs calculate 4 values. We may or may not need all 4 of the values. In our case, in training weights, we take the average and we just need that average value, and we need that average value to be uniform among all the GPUs. We don't really need all 4 values to be stored. Next, please. So the reduction operation can be any reduction operation. It can be sum, it can be multiplication, it can be max, it can be min, or it can be average. It depends on the application. Next, please. In our case, it's average. Basically, in the cases of training models, it's mostly average. Next, please. And to give you a small basic overview of how the weights are actually calculated, I have tried to make it as visual as possible. So one of the very commonly used algorithm for all reduce to communicate all the weights to all the GPUs, please assume that our setup has 4 GPUs, and all the 4 GPUs have calculated an array of 4 weights. Labeled A, B, C, and D, as you can see on the screen. So what will happen during the first all reduce cycle is that worker A will transmit weight A0 to worker B. Worker B will transmit weight B1 to worker C. Worker C will transmit C2, and worker D will transmit D3. Now all the workers after, oh yeah, Zishan, please go ahead.
How often do we do this operation?
So we need to do two all reduced cycle for tensor parallelism. We need to do two all reduced cycles per layer per batch. So basically, after every layer in a tensor parallelism, for every forward pass, we need to do two all reduce, and for every backward pass, we need to do two all reduce.
Then do we need to do all reduce for data parallelism or pipeline parallelism?
The paper didn't mention it, and so I don't think they would be required to. But I am very sure that tensor parallelism definitely requires all reduce.
Okay, yeah, sounds good. Thank
Oh,
you.
and regarding data parallelism, so remember the part where we aggregate all the weights, data itself is a all reduce function, like we're taking the average of all the different weights on the GPUs. So that would occur at the end of each batch.
Good point. Yeah, thank you.
Right. Thank you for adding that, Yalu. Next, please. Right. So from the previous cycle, if you can visualize that, worker A received D3 from worker D. So now for the third index in the array, worker A will store D3 plus A3. Now worker A can transmit D3 plus A3 to worker B, and worker B can save that in the third index of the array. Similarly, worker B will transmit A0 plus B0, worker C will transmit B1 plus C1, and the cycle goes on. This cycle goes on till each and every worker has all four values for all four indexes of the array, and then those values are averaged. And basically all four GPUs get the average value for the weights this way. So that is what goes on for an all reduced cycle in the backend. Next, please. Right, now we actually come to the analysis part. So oftentimes it's not just pipeline parallelism or just tensor parallelism that is being implemented for a model. Most of the times tensor and pipeline parallelism or other forms of parallelism are implemented together. So in this section, we will be analyzing when tensor and pipeline model parallelism are implemented at once. Next, please. So as I introduced before, P minus 1 whole divided by M is the bubble time. What you must also remember is in our setup, the number of GPUs, which is given by small n, is actually equal to the multiplication of the all three parallelization dimensions, which is P times N times D. So since we're not using data parallelism here, we can set that dimension as 1, which will give us P times T is equal to N. From that, we can calculate the value of P as N over T, which will give us the new formula on the right. What we can observe here is that when value of T is increased, bubble time decreases. So this formula suggests that like we can keep on increasing tensor parallelism, and it will reduce bubble time. It will keep on reducing bubble time. Now, BSH, what is that? That is basically, just a second. So for each microbatch, and I'm talking here about pipeline parallelism, for each microbatch, the total number of communications that need to be performed between every pair of consecutive devices or consecutive GPU is given by BSH. What is B? B stands here for the batch size, so batch size of one microbatch. S is the sequence length of the input, and H is the hidden size, basically the size of the hidden layers of the neural network. What are hidden layers? The first layer of a neural network is called the input layer. The last layer is known as the output layer. All the layers in between are known as hidden layers. H is basically the size of the hidden layers. So the number, as I mentioned before, the amount of communications in pipeline parallelism that need to be performed between each pair of consecutive devices is given by BSH. Next, please. But for the total number of communications that need to be performed between each GPU, every layer is given by 8 BSH times T minus 1 whole divided by T. Now, this is because of the all reduce function that I discussed before. Yes, Zishan, please.
I don't think H refers to hidden states, but it does not mean the hidden states of all layers. I mean, hidden states is equivalent to embedding dimension. Is how the vector size you embed to represent a token. It's a token representation.
Right. Okay. Thank you so much for that correction. I'm really sorry about that.
I have another question. You repeatedly mentioned about bubble time. Can you say explain why bubble time is bad for us?
Bubble time is basically bad because machines are lying idle. We have the compute power, but they're not really doing anything. So we are not using all of the compute power that is available to us. So we need to minimize that as much as possible to reduce compute time. So that is why it is extremely necessary to minimize bubble time to make our computation not only like time efficient, but also energy efficient, because as the GPUs are idling, they're still using idle power, but they're not really performing anything.
Okay, cool. Thank you.
Right. Next, please. I think this is the end of my section. Thank you so much. If anybody else has any questions, I would love to try to answer them. Thank you, everyone, for your attention.
All right. Thank you, Arnav and Yalu. It's been a great presentation so far. And so I'm just here to talk about an evaluation and conclusion for everything, and also just briefly go into more detail in this evaluation, which you're going to see next slide. So the first part of the evaluation is just considering, overall the key takeaways from this paper. And that begins with the key observation, as you can see in the graph on the bottom right. The orange lines were with parallelism added, and the blue lines below show how historically, when you add more GPUs, you get diminishing returns for each GPU trying to do the same task. You have lower teraflops, but by distributing the model across all the different GPU memories instead of like spending a lot of bandwidth back and forth in communication, like in data communication, for example, it leads to inefficiency. So this provides a very giant efficiency boost, especially the larger your scaling becomes. Yeah, so next slide, please. So going into more depth in this point I'm trying to make is that, typically GPUs are, contained within the server, and then these different like servers or nodes are also trying to talk to each other, and those will have multiple GPUs inside them as well. So within the node, you might have multiple GPUs talking to each other with technologies such as NVIDIA's NVLink or AMD's Infinity Fabric. And these are very high bandwidth because obviously the distance is less. And then internode communication happens over protocols such as MPI, for example, or something else. And when we implement pipeline and data parallelism, what happens is the communication load with additional, there's additional commands such as the forward and backward passes that were mentioned. These add to the communication load, but they reduce the actual like they reduce like other loads. So it leads to like a balancing act that needs to be made. So it becomes increasingly important if we want to implement something like this to have strong network infrastructure, and we want to have GPUs with higher communication frequencies specifically, or higher communication bandwidth if we want to implement parallelism. Um, And so we see that, the takeaway from here is that when you have smaller like numbers of GPUs, this extra communication load that's being introduced by parallelism may not be worth the marginal benefits. But it depends on other factors such as the size of the model, how much GPU memory you have, and other things. And with large number of GPUs, again, it still depends on the same factors, but the balance shifts towards parallelism almost certainly being the better way of implementing this. And as Zishan mentioned in the chat earlier, this type of parallelism we're mentioning has become the industry standard for training models. And so it's quite clear that the extra communication overhead is well worth the performance improvements. And we'll go into this a little more in the upcoming evaluation. From the research paper, we see that pipeline parallelism, the efficiency improvements you get are more pronounced with higher levels of GPUs, not PUGs, sorry, and larger batch sizes. So with 384 GPUs, the research paper identified like a 6.6% performance increase. But when you 7x the GPUs to 2240, you see a 10x improvement in efficiency. So it becomes 70% more efficient to have your model distributed across different GPU memories and to have parallelism going on. And so specifically, it looks like pipeline parallelism is the most efficient improvement, but all improvements identified in the paper do add up to have a larger impact. And now I want to flip the lens a little bit and see whether everything we explored, whether this can be useful to us preparing for SCC24. The first thing we realized is that the number of GPUs tested anywhere in this paper, the smallest number we saw was 32, which is still higher than the number of GPUs our cluster is going to have. However, every improvement counts, and we still have the potential to improve our performance by implementing these changes. This is something that we will probably have to spend some time testing and seeing, on the balance of, extra communication versus extra, data access or something, what's best for our hardware. But it's something to test and find out. And then additionally, a caveat is that Megatron LM would be on its own difficult to implement on AMD GPUs because it was specially designed for NVIDIA GPUs. However, Microsoft maintains a Megatron DeepMind, which is not as efficient as Megatron LM, but this does have documented support for AMD GPUs. So it's not like we would be starting from scratch, and we would have some level of support through, for example, GitHub documentation or other things. And so in conclusion, the techniques here represent a mix of benefits and challenges for us. As mentioned, with regards to balancing, communication or information with data so that the key goal is, make sure our resources are not left underutilized, which is, is bad for performance, it's bad for the environment, and so on. And so this represents an opportunity for us to also see if we can move to maximize performance and maybe implement industry standards. But of course, it'll depend on our specific node or cluster setup and whether we're even at the size that might benefit the most from implementing these changes. And thank you so much for staying on for so long and for listening to both of these presentations. And thank you, Henry, Yalu, and Arnav as well for all of your work on this presentation.
Wow. Thank you, Ruth. Very good presentation. I really like your conclusion and your evaluation. Very good point. Well, good work and good job. Yes, great. The presentation is great. Well, yeah, I have a few questions regarding your evaluations. There are a few points that I want to bring up. Well, first of all, you mentioned, first of all, there's a big communications for deploying all these different parallelism, model parallelism, sorry, data parallelism, tensor parallelism, pipeline, sequence, etc. And all these requires very high bandwidth for inter-GPU communications. And in your opinion, what do you think? And especially given that both of the papers are focused mainly on training part, what do you think? How would these parallelism schemes will be applicable to MLPerf inference benchmarks? And under what conditions will these parallelism be applicable?
Yeah, thanks for that question. So I might be wrong, but I think the main benefit, as you mentioned, of course, there's a lot of heavy communication going on, but specifically for MLPerf inference, the main benefit would probably be in cases where even the model we're trying to do inference on is still so big that it doesn't fit into GPU memory. It might be a good idea to deploy parallelism and have chunks of our, computations happening, and then adding these forward passes, backward passes, and so on. Even though they add some communication overhead, it would be better than, for example, having to use swap memory or having to, have other sorts of memory struggles and slow down the entire system.
Okay,
Right.
adding on to your point.
Just one point to that.
Sorry,
if you're doing,
also,
sorry,
please go ahead, Professor Chen.
I was just going to say, if you're doing inference, you don't have to worry about the backward passes.
Yes.
So a lot of the bubbles that you're showing in the pipeline are especially there because you're going forward and backwards is very hard for pipelines to do. But if you're only going in the forward direction, you can get much better utilization. The thing to look out for, though, is each stage has to have an equivalent amount of work. So if some stages have more work than others, then you get bubbles. If you can divide the work evenly in pipeline parallelism, then you'll get much higher utilization.
Oh, yeah.
No.
Thanks for sharing. Or
Pipeline is passing for stage 1, we are passing from GPU 1 to GPU 2, and GPU 1 could be idling.
yeah, if the stages are unequal in work, right?
Yeah. Okay. Yeah, that makes sense.
But anyway, it's not an easy thing to do. I'm just pointing out that you don't have to worry about the back propagation. So
Yes.
your bubbling should be much less dramatic than the pictures that we're showing earlier.
Yes. Adding to your point, right, that because we do not need to store the activations, so that the memory requirement is less for training. So we do not, so it's not too heavy loaded in terms of memory. And back to you, Arush, do you still think that storing the model will be a memory bound issue?
Oh, I guess for inference, it might not be as much of a memory bound issue, based on what I just learned here.
And in what models will we have to deploy all these parallelism schemes?
I guess it would mostly be needed for training with
No,
very
no, I
large
mean
models or very
MLPerf
large levels of
inference.
parameters. Oh, like Meta's Llama 70B, I believe, is
Exactly.
like a very giant model, but for example, Mistral or other ones, they tend to be significantly smaller, so it may not be needed for those.
Yes, if they're, well, because for AMD GPU specifically, the inter-GPU communication is less than what NVIDIA provides. So would it be more beneficial to just do data parallelism? Because we already load the model onto each GPU and then we just give it the data and we will not have any bubble in the middle. What do you think?
I think, yeah, it would probably need testing, but I agree with you. I think that might be the most efficient or the most beneficial way for us to make use of this information and for us to maximize our performance.
Cool. And adding on to your point, actually, we do not need to empirically test. We can, calculate the activations with the previous presentation and to calculate what is the memory required to pass and to train. Now, with all these, we can empirically calculate theoretically calculate what is the memory required and how long it takes to train and pass.
Okay. That doesn't sound like fun math, but I think you're right.
Also, I have another question for Zixian. So you said that you think pipeline parallelism is not as good as the tensor parallelism, but in the research and in the evaluation, it showed that pipeline had a better improvement. What do you think this might be down to?
Pipeline parallelism is better. When did I say it is worse than tensor parallelism? I don't remember.
I remember you saying something about not liking pipelining parallelism.
Oh, probably I was talking about data parallelism. When I was answering Arush, is that what you're referring to?
Never mind, it's further up.
Okay,
I think it
I
really
don't remember.
depends
I
on,
may say it wrong. I mean, pipeline parallelism is great.
but it's highly dependent upon making sure that the work is evenly divided. So
Yes.
I think that's probably part of the
Also, another
difficulty.
question regarding MLPerf. Will the data input that we need to process be like do they need to be in sort of a chronology? Are they times? Do they have a specific time sequence in which they need to be inferred?
I mean, they will load as much as you need them.
No, what I meant was something like, let's say if we're reading a passage of text, then there is the importance to the order of which we reading individual words. Whereas if we're just reading a bunch of images, not a video, but images, then it shouldn't matter too much the order in which we're reading the images. I'm asking in terms of data parallelism. So because if we want to read the words, have them do it parallelly, then with that,
No, I mean, data parallelism means I'm sending, let's say, it is basically batches and macro batches. So instead, well, let's say I have 10 data points and I want to do data parallelism. I split the 10 data points into 5 and 5. I feed the first 5 to the first device, second 5 to second device, and each data point is still a complete sentence.
oh, I see. Never mind.
Oh, you cover data parallelism. Why do you ask that question?
I just thought that when we're dividing things up, we might be breaking some of the let's say chronological information that may come Because let's say if we're reading an entire chapter of the book, if we're just breaking things down into pages, we might still be, missing some of the connection between a couple of pages if we're just doing data parallel. So
the data will be within your model's context window, so you do not need to worry about that.
Okay, I see. So the smallest micro batch that will be breaking down the data into will still preserve basically most of the contextual information, right?
Yes.
I also had a quick question, Zishan. Yalu, could you quickly go to slide number 9, please, since our thing is still up? I actually noticed this like while we were presenting, and slide number 9, please.
Mm-hmm.
Yeah. I noticed this, as I said, while presenting. Is there a specific reason why each back pass is shown to be exactly double the time of each forward pass? Like, is there a reason why back passes are take more time than forward passes?
Yes. Yes. Very good point. So when we are in the forward pass, why it is, let's say 1, is because we only do multiply operation, right? And that is one floating point operation. But when you are doing backward, you are also multiply by the gradient and you add it to the update the weight. So that is multiply and add. So that is 2 flops.
Right.
Yeah. So that is why, backward is twice. Yeah, very good question.
Right.
Right. Do we have any more questions regarding large-scale model training? Well, if not, thank you for listening to our presentation. Yes, Professor Chen?
I was just going to say thank you, everybody. It was great. Both presentations were awesome.
Thank you, everyone. Very good, very, very, very great work. And I believe this not an easy task, especially that you just finished Transformer within 2 weeks. And then now we're diving into some very advanced model parallelism topics. Very good work. And thanks everyone for your attention and your hard work.
Hey, everyone.
Great job, everyone.
And MLPerf Group, don't leave yet.
Yeah, I'll leave.